Hi, welcome to this new webinar about the generator synchronization. So while we are waiting for people to join in, we still have lots of people who are not connected. I will once again, for those of you who have seen the previous webinars, repeat some basic information about the GoToWebinar interface and how we will proceed. So if you look at the right side of your screen, you will see the GoToWebinar controls, and you will see that in there you have a few tabs, one of which is named question. So it's a gray bar with questions appearing on top of it. This is where we want you to input all of your questions so that we can answer them either by in a written form or verbally. So to this end, I have with me again tonight my dear colleague Gonzalo Mora. Good evening, or well, good evening for us, and hi, Gonzalo.
Hello, good evening, Christian, and good morning for South Pacific and the Middle East. Welcome back to this new webinar about generator synchronization. So same as the webinar we did last time we were together, I will be using the chat and answering your questions. And if the questions are for Christian, I will pass the question to Christian. So welcome back, and Christian, you may start when you want.
Thank you, Gonzalo. So once again, while we wait for everybody to join us, I will finish presenting this interface. So apart from the questions tab, you will also see a chat tab. So this is where we want you to input any other comments or info that you want that is not a question, because the distinction between the two is that the questions are recorded so that we can get back to you if we are not able to answer the question right away, while the chat is totally free and not recorded. So please use the chat for any information that is immediate and does not require follow-up. Then you will also see a handouts tab under which you will find three handouts that we actually provided to you. So you might as well download them right now. So you will find the PowerPoint file that I will be using for the presentation, the data sheet for the EMS training system that the simulator that we will use tonight is based on, and finally the form that needs to be filled if you want to get a free license for this simulator, LVSim EMS, if you don't have it yet. And finally, you will also see in your interface that there is a round button with a hand icon on it. So we might at some point ask you to answer a yes, no question by raising your hand. So this is what this is used for. Okay, so while we wait still a little bit for people, I will just ask you a few questions here through a poll that will appear on your screen, just so I can evaluate your background knowledge about the topic we're about to cover. So first, I will ask you, that's it, how familiar you are with the working principles of a synchronous generator, because this is what the topic, what we will discuss about tonight. So once again, I warn you, some of you will not be able to vote because the interface of GoToWebinar has some issues apparently with this feature. But about 2 out of 3 people should be able to vote. So if you click and nothing happens, that's unfortunate. Sorry about that. Thank you for your answers. And now I will provide you with another question. The next question is about if you are a teacher and you have ever performed an exercise of generator synchronization with your students. I would like to know if that's the case, because you will be more aware of the issues and what needs to be done and what can be taught through this kind of exercise. Well, I can see that most of you have not had a chance to do that with their students, so I'm glad that this will be a new opening for you this webinar, you will see that it is really easy to perform with LVSIM, as well, of course, as with the actual physical EMS system. And it's really, really a valuable exercise for your students to understand many, many things about synchronous generators. So thank you for all of you who voted. And even if we are still missing lots of people, I think I will start right away because, well, we are already 5 minutes in the webinar. So welcome again to this webinar about not three-phase rotating machines, as you can see on your screen, but about generator synchronization. The reason you see this title here in my PowerPoint is simply because this exercise about generator synchronization is extracted from our three-phase rotating machines course, which comprises many, many exercises, generator synchronization being the last one of these exercises. So that's where this comes from. So what will be our program today? Well, first of all, we will look at, we will have a theoretical discussion of synchronous generators and generator synchronization by looking at the working principle of a synchronous generator and then the 4 prerequisites of synchronization. So what are the conditions that must be met before we close the contactor that will electrically link our generator with the network? Then so this will be the theoretical discussion. Then we will dive into three parts of a single hands-on exercise. First part about synchronizing the generator itself. Then once we are synchronized with the network, how can active power exchange with the network be varied? And then how can reactive power with exchange with the network can be achieved also. And all these exercises will allow us to present you yet some more new features of LVSIM EMS that we have not explored over the last 2 webinars. So the first one of which will be a computer control of the dynamometer. So you will see what I mean by that. Of course, we are running a simulator, so it is computer control, but we will see what is the distinction between that and the other way we have been using the dynamometer up to now. And also we will look at the synchroscope, which is another really specialized tool that is expressly made available for the exercise we will be doing together today. Okay, so let's start with the working principles of a generator. So of a single, really simple, basic generator here, and then we will extend that to a 3-phase synchronous generator. So of course, as you know, a generator works on the induction principle, whereas if you have a current flowing through a loop of wire, you will generate a magnetic field. And if you have a change in magnetic field in an enclosure, the variation of the magnetic flux will induce a voltage in coils of wires that are exposed to this change of magnetic flux. So as we can see here, we have a rotor that is mounted on a shaft. The rotor is made of a coil of wire, and this coil of wire can be fed a DC current by the contactors here, the brushes, the collector that we have here. So as you can see, we apply a DC voltage to this collector, and this will send the current through the coil, which will in turn generate a magnetic field in the middle of this coil. And of course, this shaft is turning. So this is happening while the shaft is turning, so while the coil of wire is turning. Since the coil of wire is turning, the magnetic field that is generated is constantly changing for the magnetic core, the soft iron core that is here, which is really receptive to this magnetic field. And around this iron core, we have coils of wire. So as the magnetic field changes, the coils of wires here are exposed to this change in magnetic flux, and a voltage is induced in the coils, which is collected here at the 2 ends of the coil. So by rotating this rotor, we are generating a sinusoidal, so a varying magnetic, sinusoidal voltage at the output of the coils, as we can see here on. So it's not a pure sinusoid because of the mechanical intricacies and the way the coil is done and all that. There are different ways to achieve a better, closer to sinusoid signal, but this gives you a good approximation of the type of voltage we will get at the output of this simple generator. Of course, now we can extend that by, instead of using a single pair of poles like we had in the previous image here, so we have a single pair of poles. If we extend that and use instead 3 pairs of poles, as we can see here, well, it will be possible to generate 3 voltages at the output, and they will all be shifted by, of course, 120 degrees compared to one another, because if you have 3 pairs of poles like that, the total, so 360 divided by 3 is 120. So each of our phases will be phase shifted by 120 degrees. So the way this works is that, let's imagine that our magnetic field generated by the rotor is maximum in the vertical direction here. I will have maximum induction in my A phase, which will give me a maximum positive voltage when the magnetic field is oriented like that. But then the rotor keeps spinning, arrives here, the maximum is here. If you look closely, you will see that the coil here is reverse in direction than this one. So this will induce a maximum negative voltage in my C pole, then to B for a magnetic positive, then to A for a negative, a maximum negative, maximum positive on C, maximum negative on B, which eventually yield 3 voltages at the output like this. So as you can see, the same sequence we just looked at: maximum positive for A, maximum negative for C, maximum positive for B, maximum negative for A. So we can see that we get 3 sinusoidal voltages like that at the output of our generator. So this is how 3-phase power was born, by having these multiple pairs of poles in the stator of a generator. Of course, in a real industrial generator, we will have many more than 3 pairs of poles, because the more we have, well, of course, the bigger the generator, the more we can fit in the space. And the more we have, it means that the more cycles of voltages we will be able to produce with a single turn of our rotor. So as you can see here, a industrial generator can have well, first of all, can be really, really big. You can see a table at the back there. So a human would be about that size here. So you can see the size of this thing here. And it generates 350 megavolt ampere. So quite a good amount of power out of this generator. So this is it for the working principles of a generator. So it's really a quick introduction to the topic, so we can better understand what will be happening in the upcoming exercise. So the exercise itself is about generator synchronization with the network. So what is this? Well, first of all, you have to understand that whenever we want to connect a generator to produce power to push on the power grid, well, it has to be done in a specific way. So the generators, for example, in a hydropower plant, let's say that hydropower plant has 6 big generators, one beside another, that can be turned on and off depending on the needs. So these generators are not all connected to the network at the same time. They will be, as I just said, depending on the needs, they will be connected to the power grid or not if the needs require it. So whenever a generator starts to spin, we will bring up to speed, and then we will check that the conditions are required for the generator to be linked with the network before closing the switch, closing the contact that will electrically connect the generator with the network. And this is what we will be looking at first here. We will be looking at the generator synchronization and the requirements, the prerequisites for this to happen. Then we will look at how we can achieve synchronization manually. Of course, nowadays everything is done electronically, but we will have a better understanding of what is required by doing it manually. Then in the full exercise, there is a question about the electrical transient and the mechanical stress on the generator at synchronization time. Unfortunately for us, we won't have time to go through this specific topic here, but it is part of the exercise that you can go to in our manual if you want to try this by yourself. And finally, we will end the presentation with the generator operation after synchronization. So once we are connected to the network, what does happen with our generator if we play with different parameters of this generator? Okay, so first, well, in fact, before going into that, do we have any questions up to now, Gonzalo, or any comments about technical problems?
No, everything is fine. We don't have any comments additional here. The only question that I have is about licensing. One teacher is asking if they need to purchase an additional license for the teacher, or they can share the licenses with the students.
That's interesting. I had the exact same question this morning. So in fact, you have to be aware that our licenses are floating licenses. Okay, they are not attached to a specific person. So if you buy 30 licenses and you have, let's say, 30 students, in fact, you know that out of your 30 students, they will never be all connected at the same time. So there will always be some licenses that are free to be used. So you have 30 licenses to be connected at the same time on our software, on our server. So as long as you don't have more than 30, it can be you, it can be your students. There is no distinction between the teacher license and the student license. So typically, since it is concurrent licenses, a school will not buy as many licenses as they have students, of course. So let's say that you have a school with 400 students. You can buy just probably something between 50 and 100 licenses, and you're more than sure that you will never have that many students connected at the same time on our software. So that's the way our licensing works.
Perfect. Thanks so much.
You're welcome. Okay, so what are the 4 conditions that must be met before we close the contactor between our generator and the power grid? Well, first of all, we have to make sure that the phase sequence of that is produced by our generator is the same as the phase sequence that is produced by the network, that is used by the network. So for example, if I go back to my slide here, so we saw, well, in fact, this one here. So we see here that our phase sequence is first phase A, then B, then C, and then we repeat A, B, C, A, B, C, okay? So if our generator produces the reverse sequence, which would be ACB, and it is connected to a network that uses ABC, then of course you don't want to be in this power plant when you close the contactor, because the generator will simply explode and there will be lots of damage provoked by that. So of course, the first thing you have to make sure is to have the same phase sequence. How can the phase sequence be reversed? Well, simply by changing the sense of the direction of rotation of your generator. So if a generator spinning clockwise produce ABC, if you spin it counterclockwise, it will produce the reverse sequence. So we first have to make sure that we produce the same phase sequence as the grid. The second condition to be met is that the output frequency must be equal, of course, to the AC power network frequency. So for us in North America, we're speaking 60 hertz, and for the most of the rest of the world, it's 50 hertz. So Europe and Asia, well, in fact, some parts of Asia is different, but 50 or 60 hertz, basically, that's the frequency you want to get out of your generator. And of course, for good reasons, we have to be in sync with that. Then the third condition that must be met is that the voltage output of your generator must be equal to the AC power network voltage. So of course, a generator never works with low voltages like 120 or 220 volts. We are in the kilovolts, but let's suppose that our generator is producing just 120 volt, and you have to make sure that it is exactly 120 volt, because that's what the network is expecting. So the voltage output, which is represented here by the blue curve, which is the output of my generator, must have the same amplitude as the voltage of the network. So we can see here that it's not exactly the case. We can see that we have a small difference in voltages, so we would have to correct that to be able to achieve same voltage at the output of our generator. And finally, the last condition that must be met is that the two voltage curves must be in phase. So right now you can see in my oscilloscope output here that the generator output and the network voltage are not in phase. So there is a phase shift between the two. And if I was to close the switch with a real generator, mega volt ampere generator weighing multiple tons, if I was to close the switch in this condition where I have about a 90-degree phase shift, again, the generator would just explode. Okay, so of course we have to, because the mechanical stress on the generator would be much too high, as we will see in a moment. So we have to make sure that in the oscilloscope view that the two curves are on top of one another before we close the switch. We will see that we have other tools that allow us to check that we are in sync with between the generator and the network, and we will see that in a moment. So these are the four conditions. If these four conditions are met, then you can close the switch that will electrically connect the generator to the network. So how do we achieve that? Well, it's really simple, as you can see here. On the left side, you have the synchronous generator that is connected to the AC power network on the right side, but they are not directly connected. As you can see, the lines are going through this the synchronizing module, which comprises a three-phase contactor. As you can see, this is the three-phase contactor here, the parallel lines. So this electrical contact will be closed only when we close the synchronization switch here. So we will be able to monitor the voltages on both sides, make sure that they have the same frequency, the same sequence, the same voltage amplitude. And once all these conditions are met, we will close the switch to connect them electrically. And to assist us in knowing the proper condition, if the proper conditions are met, we will use a couple of tools. So we will use the synchronizing module, which, as you can see, comprises also 3 lamps. So the lamps, if they're off, they will tell us that we have the same voltage on both sides of the synchronizing module. If they're on, it means that we don't have the same voltage on both sides, and we should not close the switch when the lamp is on. And finally, the other tool that we will use is the synchroscope. So the synchroscope will not tell us if we are in phase. Well, it will tell us that if we are in phase or not in phase, and it will also tell us if we are generating the same frequency as the network. So depending which way it turns, we will see in a moment that it tells us if we are producing a frequency that is higher or lower than the frequency of the network. I forgot to present to you this little coil here, which is our field coil. So the 8 DC current that we feed to our rotor, to our electromagnet, basically to generate the magnetic field that spins inside the stator to generate this 3-phase output. So this is our field current here. So synchroscope, here's what a synchroscope looks like. So as you can see, it's made up of a needle and a degree rating all around the synchroscope, telling us by how many degrees our generator voltage is phase shifted compared to the network voltage. And at the same time, the direction the needle is spinning will tell us by how much and in which direction is our frequency different than the network frequency. So for example, if the generator generates, let's say, 59 hertz and the network is at 60 hertz. So if I am below the network frequency, the needle will spin counterclockwise, okay? And the greater the difference between the two frequencies, the faster the needle will spin. Okay, so if I am at 55 versus 60, the needle will spin really, really quickly. If I am at 59.5, it will spin slowly. Same thing in the other direction. So if my generated voltage is at a higher frequency, the needle will spin clockwise. Is that the last one? No, sorry. So here, the previous one here is about what happens if we close the switch to link our generator with the network while the two voltages are not in phase. So we can see here mechanically inside the generator what it looks like. So let's say that the blue arrow represents the current orientation of the magnetic field of our rotor, while the red arrow here represents the orientation of the magnetic field generated by the network. Okay, so you can see that we are lagging because our magnetic field is behind. If we spin this way, our rotor magnetic field is behind the stator magnetic field, so that if we close the switch at this moment, a huge current will be sent through the stator to force the rotor to realign with the network, because the network has much more electrical inertia than, of course, our single generator. So this huge current will probably break your generator, because once again, I remind you that this rotor here weighs many tons. So if you try to accelerate it too fast, it will just break open. Same thing in the other condition here. If we are leading, so if our magnetic field is before the network magnetic field, the stator magnetic field, it will have to be broken to realign, and again, a huge current and a huge mechanical stress, huge torque on the rotor will happen. So we want to prevent that by closing the switch only when the two magnetic fields are aligned. Once we are synchronized, what does happen inside our generator? I'm almost done, by the way, with the theoretical concepts. We will dive into the exercise. So what does happen with our synchronous generator when we are synchronized with the network? Well, first of all, the blue dashed curve you see here represents the relation between the torque and the speed of our generator when it is not synchronized with the network. So of course, as we increase the speed of rotation of our rotor, the torque will also increase. So we need to put more power, more mechanical power in the rotor to make it spin as the speed increases. So that's what the blue curves represent here. But once we are synchronized with the network, we cannot change the speed of our rotor anymore, because now the speed of the rotor is imposed by the network. So once again, as I was telling you, the inertia of our single generator is nothing compared to the 1,000 other generators that are connected to the same network. So there is no way that this generator will be able to change the frequency or the voltage of the network to which it is connected. So it has to behave and stay synchronized with the network. So what does happen then if we try to make it spin faster? So let's say in our hydropower plant, we open the water vein a bit more to let more water in, which will put more power on the generator, on the rotor of the generator, which normally would accelerate, but now it cannot accelerate anymore. So as you can see, instead of accelerating, instead of its speed changing, in fact, the speed will be converted in torque along the green line here. So as we put more mechanical power in the rotor, this will increase the mechanical torque on the rotor without changing speed. But as you know, the mechanical power is the product of the speed and the torque. So if the speed remains constant, but I increase the torque, it means that I am putting more mechanical power on my generator, which in turn will be converted to more electrical energy. So as we increase the speed setting on our prime mover, or as we open our water vein or steam vein in a nuclear or thermal plant, we will just increase the torque and therefore the amount of electrical power that we get out of our generator. And then finally, the last control we have on our generator is the field control. So what does happen if we make our electromagnet that spins inside our rotor produce a greater magnetic field? So normally when we synchronize with the network, at the moment of synchronization, we will be right here on the x-axis. We will produce, our generator will not produce or consume any reactive power from the network, okay? But if we start increasing the current circulating in our field coil here, so as we increase the current, you can see that we will start supplying reactive power. So our generator will behave like a capacitor because it will supply reactive power. While if we cut down on the amount of current flowing through the field, the generator will start absorbing reactive power, behaving like an inductor. So you can see that a generator, not only can it be used to produce power, but it can also be used to generate or consume reactive power. And sometimes it is used to this end instead of as a really as a generator. It is used as a variable capacitor if you want. And we will see that at the end of the hands-on exercise. Any questions before we start the hands-on exercise, Gonzalo?
There's a question that maybe you may want to answer it while you have the system going on.
Yep.
The question is, what happens if while we're synchronized, we take out the field, we disconnect the field?
Okay. Yeah, that's a really good question. In fact, well, I know exactly what would happen with the real system. I've never tried it with our simulator, so that might be something interesting to try. But of course, in real life, you don't want that to happen because then you don't have any counter torque anymore. Your generator starts spinning faster and faster, and it can again break out. So, but we might try it with the simulator during the exercise. Thank you. Any other questions?
No.
Perfect.
That's what we have up to now.
So the procedure outline here for the next exercise. First, we will start with the synchronization itself. So we will perform the manual synchronization of our generator with the network. And then the last part of the exercise is it will be to look at the generator operation after it is synchronized with the network. So in fact, this is not the good wiring diagram. I realized that I had a mistake in my PowerPoint. Well, in fact, it's not bad. It's simply that it's not complete. So I will now go into the manual that accompanies this here. So the full manual, 3-phase rotating machines here. And we will go right into the exercise that we are about to do, which is the last one, as I was telling you. So exercise 6.4. So you can see here quickly in the table of contents that there are multiple exercises in this manual: prime mover, brake operation, 3-phase scroll cage induction machine, eddy currents, synchronous motors, 3-phase synchronous motors, and finally generators, to end with the last exercise, which is generator synchronization here. So if I go to this exercise here, 4.3, here. So this is the schematic I want. And I will put it to the side here, a little bit bigger, like this. So we see here in our schematic that what we want to do is connect our synchronous generator, which is one of our motor module, generator module. It will be mechanically linked to the prime mover that will make it spin. So this will be our dynamometer. And on the right side, it will be connected to the power network through our power supply module. And between the two, we will have the synchronizing module and multiple meters, as you can see. So 1 ammeter and 4 voltmeters to be able to measure all the different parameters inside our circuit. By the way, if you wonder why we have voltmeters connected in parallels like this, it's that oftentimes we have tools inside our software that require their own voltage or current reading to perform their calculation. Okay, so whenever this is the case, these functions require their own voltage input, and this voltage input cannot be displayed in the meters. So if you want to display the same voltage, you will need to connect 2 voltmeters, one for the internal function and one for your needs to watch this value. In fact, in this case, we do not watch exactly the same value. One is the phase voltage, the other one is the line voltage. But anyway, that explains the presence of these 4 voltmeters here. So let's start putting in our module here what we need. I remind you that if you don't know which module is required for an exercise, you can go directly in the appendix at the end, which lists all of the modules that are required for a specific exercise. So right now we are about to do exercise 4.3 here. So it says that we need 1 workstation, 1 synchronous motor generator, 1 synchronizing module. So you know exactly what modules need to be put in your console. Back to page 184 here. Okay. So starting from the left side, I will start with my prime mover, my dynamometer, which I will put here. My synchronous generator, which is right here. I have to put it beside it because they will be mechanically linked. And finally, on the right side, the AC network, which is represented by our power supply. So power supply here. Underneath, I will need the synchronizing module. We have 2 versions of this synchronizing module, an older one and a more modern one. This one requires 1 additional connection. So to limit the amount of wires required, I will just use the old one. They have the same, for what we need to do, manual synchronization, they have the exact same working principle. And finally, I will add the, I will put it here. What do? I don't remember. No, here. Yeah, like that. And finally, I will put my data acquisition module that will allow us to monitor the voltages and currents. Perfect. So let's zoom in. Here, so I will start by putting the mechanical link between my 2 machines here by installing the synchronizing belt, the timing belt between the 2. Then on the connection side, here I will need to connect each phase of my synchronous motor generator to the synchronizing module. The first phase needs to go through ammeter 2. So let's do that now. So from here, I will go to ammeter 2. And out of ammeter 2, I go to the synchronizing module here. Then same thing for the other 2 phases. I don't need to go through an ammeter, so I can go directly to the synchronizing module. Here, I will do it quickly with all the same color for all the wires, but of course, it's really easy, as I showed you, to change the color of each wire, either by clicking here or by right-clicking on each wire and changing the color. So just for the sake of speed here, I will do it all in the same color. So this first side here is connected, except for the voltmeter. And on the other side, I need to connect each phase of the power supply again to the synchronizing module directly. So from my fixed 120 volt output here, phase 3 to phase 3, 2 to 2, and 1 to 1. Like this. So as you can see, the main connections are already done. What's left to be connected? One important connection is not done yet, and it's the field voltage that we need to provide to our rotor to generate the magnetic field. And this needs to be, as you can see, fed 120 volt DC. So we will take the fixed 120 volt DC output from our power supply here to feed this electromagnet here, like this. We can use the fixed output because we have a rheostat here directly on our generator to be able to control the intensity of this field. Good. So these are the major electrical connections. The ones that are left to be done are the voltmeters. And of course, yes, here I need to connect in Y my generator like this. So this was just to show you again how easy it is to perform these connections when you have the schematics beside you. But to finish the exercise, I will now load up a pre-recorded configuration file where all the wires are color-coded, which makes observing all of that easier. So here, like that. So I used simple color code. So in white is always the neutral. So everything is white. In white is neutral. It's all connected together. By the way, you see that the neutral of the power supply is also connected to the neutral point of my generator. This is really important because otherwise you will not be able to achieve synchronization. And then I use red for phase 1, gray for phase 2, and blue for phase 3 in different shades, depending if it comes from the generator or the network here. So this makes following the schematic pretty easy. And here on the data acquisition, we see the voltmeters that are connected now to be able to monitor the various voltages. Finally, I remind you that our data acquisition requires its own power source here that is turned on with this switch here so that now it is ready to start acquiring data. Okay, last thing we need to configure is our dynamometer here that will behave in a third different mode that we haven't seen up to now. Okay, so up to now we've been using the break function of the dynamometer. In the power factor compensation webinar at the beginning of the week, we used the negative constant torque prime mover break function. And now for today, we will be using this function here, either clockwise or counterclockwise, that has been developed expressly for this synchronization exercise. The reason being that we do not want to have a constant speed control because otherwise the feedback loop of the speed on our dynamometer would interfere with the generator trying to synchronize with the network. And same thing for the constant torque. We don't want to achieve constant torque either because this would also interfere with the synchronization with the network. So basically, we want a function that allows us to control the speed of the motor of the generator, but not in a strict way. So we will more suggest a speed that we would like to get, and the dynamometer will balance that with the needs it sees from the generator itself. So again, I could control it from the front panel here, but I want to show you another way of controlling our dynamometer, and that's what I said at the in the introduction, that we would be using computer control for our dynamometer. So we can come here and open this 4-quadrant dynamometer power supply control window here. Okay, we can also press this button here, which brings at the same place. And you will see that I have a window that allows me to control all the functions, but with a much richer interface. So you might wonder why we have that in this simulator. Well, it's simply because, again, the simulator reproduces exactly our physical system. So remember that in the real physical system, the dynamometer would be a physical unit sitting in a metallic console. And beside that, you will have a computer to which the dynamometer is connected through a USB cable. So from this computer, you can control the behavior of the physical module. So that's what this represents here. So I will come here and select again the exact same function I wanted to select on the faceplate. So clockwise prime mover break here. And I will enter the synchronous speed expected for my 60 Hertz synchronous generator. So the synchronous speed is 1800 RPM. Of course, in a 50 Hertz country, the synchronous speed would be 1500, so 1500 RPM. So 1800. And right there, I can start my generator spinning. So as you can see, even if I enter the 1800, I get only 1651, just like because what I told you, I'm not trying to achieve a really precise speed, but just an indication of what I want. So I will increase here the speed settings so I get closer to 1800, which is my synchronous speed. So here, I'm about 10 hertz from the synchronous speed is good. And we will now look at the various data that we have. So first, we will open our meters. And we will ask to see, we will ask to see the active power on all three phases. And here I will check at the, let's say, the frequency output of my generator, which is E2. So E2 is the voltmeter connected to the generator. And finally, here I might want to see also the reactive power. So power measured from E1, E2, E3. No, I have only E2, I2. I have only I2 connected, so E2, I2. So reactive power for my phase 1, which is connected to ammeter 2, but I want the reactive power here. So we will be able to monitor all of that at the same time. So let's start here our meters. We don't get anything. Well, for good reasons. We are not yet all powered. First of all, here, our field is not powered, so there is no magnetic field in our rotor. So we need to power that, and to do that, we need to turn on our power supply here, which will turn on the DC power on our electromagnet. So let's turn that on. Oh, in fact, I did something really, really dangerous here. I turned my power on without verifying if my synchronizing switch was closed. If it was not closed, it could have been, well, with our simulator and even with our real physical equipment, there is no risk of breaking anything. But in the real world situation, in the real power plant, you never, ever want to do that. Of course, you have to make sure that the synchronizing switch here is open. So now the power is on. I have my DC power here. I just need to turn on this here to have some magnetic field generated in my rotor. And now you can see that indeed on the E1, I see the voltage on the network side, and E2 is the voltage of my generator. So that we can see that the voltage is not high enough. So that's one condition that is not met. Another condition that is required is to have the proper frequency. So we can see right now that we are at 60, almost 60 hertz. So in fact, that's really good. And you can see here that's because my speed has increased. So I have set it to a certain value, but it has increased a little bit. So let's decrease that below 1800 a little bit here, like this. Okay. And now we will see that our frequency is below 60 hertz. So we want it for the moment, we want to keep it below just for observation purposes. So now we can turn on our oscilloscope here and look at the two voltages. So E1 for the network and E2 for the output of our generator. Turn on the oscilloscope. And now you can see that E1 is in yellow is the network voltage, and the blue one is the generator voltage. So we can see that our frequency is below that of the generator voltage because our curve is shifting leftwise. Okay, so we are delayed compared to the network frequency here. So of course, if I change the speed of my prime mover, so I'll go back to my prime mover window like this, and sorry, I get back my oscilloscope here. It's really good with this software to have two monitors, because there is lots of things to display. So now if I change my speed here to something a bit faster, you will see that the shifting really slows down, okay? And eventually I could even stop the shifting. If I get exactly at 1800, I will stop the phase shifting. So we really see the relation between that. Good. So first condition we needed to check was if we have the same phase sequence as the network, and this will be indicated by our synchronizing module lamps here. So let me decrease that a little bit here so it changes faster. Okay, so here you see that as the sine waves here shift compared to one another, my lamps turn on and off. So when the two sine waves are on top of one another, the lamps turn off. And when they are 180 degrees out of phase, that's when the lamps are the brighter. So that's the first information the synchronizing module gives me. The second information it gives me is if the phase sequence is the right one. So is it ABC or as the network, or ACB contrary to the network? I won't do it here because we are lacking a bit of time, but if I was to exchange the two wires here from our generator, you would see that the lamps, instead of all lighting at once and all turning off at once, would light one after another in sequence. This one, then this one, then this one. So it would repeat like that. So whenever you see that the lamps are lighting one after another, you know that you have a phase sequence issue, and you have to make sure that this is fixed before closing the switch. So here I have no phase sequence issue. I have a little frequency issue because my frequency is slightly lower than the network frequency, as we can see in our meter here, 59.7 instead of 60. I have a small voltage issue also because I produce only 100 volt instead of 125. So this will be the next thing that we will fix here. We will need to increase the voltage produced by our generator, and we will do that by increasing the field here. So you will see that as I increase the field, the voltage output here will increase. So increase the field here and my voltage output. And you can see on the oscilloscope also that the amplitude of the voltage is increasing. So we increase that up to 125. About like that. And now we can see that our two sine waves have the same amplitude. I have the same RMS value measured here. I have a slight frequency difference. I have the same phase sequence. So the last condition that needs to be met is to have the two curves on one another, so be in phase. The best tool to look at that is our synchroscope here, which is the last tool I want to show you. So as you can see, the synchroscope is connected on one side to the generator voltage, and on the other side to the network voltage through our voltmeters E3 and E4. So as soon as I turn that on, you will see that the needle is spinning counterclockwise, which indicate that the frequency generated by our generator is too slow, so below the network frequency. So we will increase the speed of our prime mover here. And you will see that the needle will slowly spin down. Okay, so when I get closer in speed to the synchronous speed, and when I reach the synchronous speed, well, the needle simply stops turning. So now we can see that we are exactly at the right frequency. The needle is not spinning anymore, except I have a 40-degree phase shift, phase difference here, as we can see on our oscilloscope also. So if I was to close the switch, the synchronizing switch now, it would put lots of stress on the rotor of the generator because of this realignment required with the network. So it's better, in fact, to have a slight frequency difference. So I will just decrease that a little bit here, like that. And I just wait for the needle to pass by 0 degree, which means a 0 degree phase difference between the two, as you can see on the oscilloscope also. And then I close the switch. So that's what we will do here. I will watch this needle, go to my synchronizing module. Here is the synchronizing switch. So I will just flip that when I get to 0. Next pass here. There you go. So now we are synchronized. As you can see, as soon as we're synchronized, the needle stops spinning, of course, because we have the same voltage on both sides of the synchroscope. And our oscilloscope, of course, presents a single curve because they're both overlapping. And our meters indicate exactly the same voltage for our generator and network, 60 Hertz, the perfect frequency, of course, because now it's not my generator imposing anything to the network, it's the network imposing to the generator its frequency and its voltage. So now we are synchronized. What is the last thing we want? Well, before I look at what we can do once we are synchronized. Any questions up to now, Gonzalo?
Yes, the question came back. and they don't want you to forget to disconnect the field once you're synchronized to see what happens.
Okay, we can try that right away. In fact, and we will see how the simulator behaves. I'm not sure because it's the first time I try it, and of course the simulator might surprise us. We don't know exactly the mathematical model implemented in there, so let's try
Don't
it.
worry, I have my extinguisher here, so it's fine.
We're good. Okay, so I would like to be able to watch the speed of the motor, so I will bring back my window here. And I remind you that we have a speed indication here and a torque indication. So let's flip that switch out, so which will cut the field. You see, typically we should have accelerated here, while in fact, well, it's because of our function here. Well, in fact, yes, no, in fact, that's right. Because of the function I'm using here, if I was using a constant torque function or a constant speed function, I might get an acceleration. But here, since I am setting a specific value with my potentiometer here, the dynamometer will simply try to maintain this to the specific voltage that it's sending, that it's using to have the motor spin. If I was applying a specific torque, which is compensated by the counter torque of the generator, which is normally the case in the real mechanical situation, and we remove the field, then there is no torque on the generator shaft anymore, and then of course the generator starts speeding up because of this. But in this case, because of the simulated prime mover that we're using, we don't get this effect. Sorry if that's not what you were expecting. So now by closing the switch, I will resynchronize with the network. I will force the generator to resynchronize with the network. And once again, since it is a simulator, there is no harm doing it at any point. But if it was a real generator, I would have to redo the whole process of synchronization that I just went through. Okay, so yes, what is happening now if we, I told you that once we are synchronized, we cannot change the speed of the motor anymore because it is imposed by the network. So what does happen if I try to increase the speed by turning this knob here? Well, you will see here, well, first of all, yes, so in fact, I will change that a little bit. I will just increase it a little bit here, my speed. Okay, so normally when we close the switch, the synchronization switch, what we want is this condition here, where we have no active power exchange between our generator and the network, okay? And this condition, we say that the generator is floating because it's not providing any power to the network and it's not drawing any power from the network. It's just they're looking one another and not doing anything, okay? So you will see now that as I increase the speed output of I try to change the speed of my generator. Since the speed cannot increase, what I am doing, in fact, is increasing the mechanical power I put into the generator, which turns into electrical power. So as I increase the speed setting here, I put more and more mechanical power on the generator, which produces more and more electrical power for the network. I remind you that this is the power generated on a single phase. So this would be multiplied by 3 for our 3-phase output. So that's the thing. If I reduce my speed setting here below what it was at synchronization time, now you will see that the power becomes negative, which means that my generator is not producing power anymore. It is consuming power. So now my generator is not working as a generator. It's working as a motor, and it is powered by the network. So the network is having our generator spin. And of course, this is a really undesirable condition. So whenever this happens, because, for example, the generator has lost its mechanical power, the water that is not coming in anymore or no steam coming in, we will shut off the generator, disconnect it from the network because we don't want to start consuming power from the network. Then the other thing I wanted to show you while we are synchronized and floating is the reactive power. So you can see here that I have a display of my reactive power at the generator. So once again, really, really small, not really any exchange of reactive power between the generator and network. But what does happen now if I change the field current in the generator? Well, we saw in the theoretical part that I should be able to change the reactive power by playing with the field here. So if I increase the power, the current flowing through my field, you can see that the reactive power is increasing. So just like we saw in theory, now our generator is behaving like a capacitor, and it's producing reactive power for the network. So it's providing reactive power to the network. And in the opposite, of course, if I decrease the field current, I will start consuming reactive power, which means that my generator is now behaving like an inductor. Okay, so as you can see, we can use a generator as a variable inductance or capacitance that will allow us to absorb or produce reactive power to do power factor compensation. And sometimes synchronous generators are used for this purpose in a plant. So they will be fed more or less current in their field current, and will be able to correct whatever power factor present in the plant. So basically, that's what I wanted to cover with you today. We're right an hour into the webinar, except that I would like to take some of your questions if you have any questions for us now.
Yes. What happens if we increase the torque applied to the generator, and once the torque is higher than synchronizing torque, then we start playing with the bars, with the field?
Yes, we can do both, of course. It will just, both are independent, in fact. So you will see that I will simply have a certain amount of active power here. And at the same time, I will be able to play with the reactive power output or input. And as you can see, changing the field here does not impact too much the active power. Well, maybe the simulator is not perfect in that, because typically in our in a real motor, we should have more of an impact on the active power produced. But you can see that both are, I can vary both the reactive and active power at the same time with these two controls.
Okay, here I have another question that is, does session 1 and session 2 cover the same topics or different topics? I may answer this directly.
Yes,
the
please.
same webinar will be covering the same topic. What we have is this same webinar in 2 different schedules for 2 different parts of the world. So
Exactly.
Yes, I'm sorry about it, because I know you want to learn more and share more with us. That's the bad news. But the good news is that we're going to keep on doing this kind of webinars during this week and next week. So we're going to have other webinars with some other
Topics.
subjects and some other topics. Perfect.
Yeah, so of course we're just scratching the surface of all these topics. We know that you might want to go much farther, but also be aware, because I had a few questions, really precise technical questions about the mathematical model of our motors and all that. You have to be aware that this simulator is really good. It does really well what we ask it to do, which is allow you to reproduce all the exercises for the physical version of this system in your virtual lab. But it's at the same time, it's not a research tool. Okay, so it's not an Opal RT simulator which calculates every single parameters with 5 digits precisions and all that. So it's not a research tool. It's really more for teaching the basic principles of electromechanical systems to your students. And if you want to go into research, then you would need a more powerful simulator with multi-$1,000 CPU power behind to be able to run the simulation at full speed. So this is the kind of limitations of the system.
Okay, got another question that says if we can have the video about this presentation, and the answer is yes. In a few hours after a certain processing we have to do, you will receive the video link, and you can download it and watch it as many times as you need. Or you can share it with your students if that's the case.
Yes. In fact, it's a full day. So a day after right now, at the end of the webinar, this is when you will receive a follow-up email, which contains the link to the video. Okay. So welcome again for attending this webinar on this time generator synchronization using LVSIM. I hope you enjoyed it, and in fact I will measure that, if you don't mind, by asking you again to answer this little poll, which will allow me to justify my salary to my boss. So please tell us if this webinar was useful to you, and if we are on the right track to help you with your students and your virtual teaching.
Oh, great. We have a lot questions. That's
Yeah,
good.
excellent. We're really pleased with that. So super. Thank you for attending once again and for your good questions. So as you know, we're finishing with this topic this week, generator synchronization, which we repeat tomorrow at different times. And then next week, we will dive into additional topics, power electronics, which will not be done with LVSIM anymore, because as we said last week, power electronics is not available on LVSIM, unfortunately, so we will be using the actual physical system to do this webinar. And then we will also have another webinar on process control, where we will introduce another simulator that we have, our LV ProSim simulator, which allows to simulate closed loop control of a process. So please stay tuned, go to the webinar schedule and register to these additional webinars. Thank you again for your attention, and thank you, Gonzalo, for your help.
My pleasure. Thanks so much. Good morning for you, and good evening for you, Christian.
Thank you. Good night to you, Gonzalo. Bye-bye.
Bye-bye.